Camshafts bring the complexity to an engine like no other, but we're going to try and break it down today. Let's go. All right, guys, welcome back to another induction series. Today we're doing camshafts. And again, just want to thank everyone for the comments. Thank Einstein Motors. We've got more stuff happening, a bit more direct with Einstein. I've got a manifold building series coming up, so how to build a tunnel ramp. And maybe tomorrow night we might be releasing the first episode of the mathematics and science behind how we go about building a tunnel ramp, because we've got two engines that are very, very similar. So I thought I'd do it on both of those to give you an idea. And if you like the series, we might expand it, but it will give you a little bit of an idea of what actually goes into the analysis before we even start building a tunnel ramp for a customer. We've got a drag weak engine and another drag car from down south. So keep an eye out for that. But yeah, I just wanted to say thanks for all the comments, but I can see a few people are struggling with the fundamentals, understanding what's actually happening, especially around dynamic compression and LSA and duration and stuff like that. So we're going to be breaking down a couple of theories today to help you understand that. I'm also going to put a link into Dave's video. I can't remember the episode, but I will find it and I'll put it in the description from Skunk 2 Racing. Again, every now and again, you watch stuff online. I get tons of stuff sent to me by other people. Jake, check this out. And you know straight away their level of understanding around ICE engines. And Dave is really, really switched on with the camshaft. Obviously, he's got a Spintron. He's spent many years on it, developing his own camshafts and stuff like that. And I was super, super impressed. And I really had to share it because he really gets it. And as soon as he started talking about leakage and everything, I was just like, oh my God, finally. Because in Australia, I've really struggled with a lot of people. It's like, oh, you know, stage 2 cam, this, that. And a lot of them aren't great. No, they're getting better, don't get me wrong. But especially, you know, the 2000s and 10s, you know, it was a 272 with 8.5, 9 mil lift or whatever it was. Hugely long ramps and stuff like that. And what we learned even in the NA game, because I was doing, you know, circuit engines and you know, cup cars and all different sort of stuff I had my hand in. I like to help a lot of different series, but you look in the cam book and even the difference between advertised duration and at 50, you could see some of these profiles were so lazy and they're just bleeding off that dynamic compression. Dave actually talked about this leakage problem, and you see it in LSAs, you see it in dynamic compression as well, both sides of the camshaft, both sides of the ramp. And now we're starting to get into asymmetrical profiles. So the front of the ramp isn't the same as the rear of the ramp. And we talked about last week about dual plane camshafts. And some of the math of that has changed. A lot of guys will say anything under 70%, you need to start adding more duration. But with the new chambers that are coming into some of the 2-valve stuff, there doesn't need to be as much exhaust duration compensation. Some of the guys are talking, you know, 8, 10, 12 degrees in the early days. Now with the chamber, again, this is why I say we need to look at LSA, because LSA and that exchange rate and how efficient the chamber is. So a wedge head will be nowhere near as efficient as some of the modern LSs and the Fords and what I talk about tomorrow night with the big block 9 degrees and some of the like Blue Thunders and stuff like that have an absolutely beautiful discharge coefficient. They have a really nice chamber. There's no dead areas. They fan out off the top of the valve angle. Absolutely beautiful. So their exchange rates are much faster. They're smaller combustion chambers, which means we don't need as much ignition timing advance, which means we make more horsepower and so on and so on. But yeah, check Dave's video out. He talks about this. We had a really good example probably about a decade ago when I was designing 2Js and RB camshafts. I did some 264s and 272s, but with more lift, we shortened that major and minor ramps up. So we really got it up on the 40 or 50, depending on how you want to measure it, much quicker. And even the nose radius we were broadening, and Sometimes when you look at area under the lobe, if you include a lot of that rubbish, the area won't change. So I tend to look at my at 50 area, and we're actually getting more area under the lobe as well. And these things were making better horsepower. We had better dynamic compression. The boost thresholds are lower because, again, remember, the turbo is driven by X amount of force coming out of the cylinder, X amount of bang. We need to create that. So the LSA affects that, but also the dynamic compression affects that, because the more duration we have that closed, the higher the cylinder pressure is going to be, the bigger the bang, the more gas that goes out and hits that turbine and turns it up. That's why a 10-to-1 engine, exactly the same, everything will boost sooner than an 8-to-1 engine. That should be obvious. So this is where the dynamic factor and LSA all come into it. But Dave talked about this leakage and really, really long ramp. So we would see it in cup cars and stuff like that. We'd look at different camshafts because we used to use different masters and put them on the same profile and then set our LSA. And most good engine builders do this day in and day out. The average guy probably doesn't know, hence why I'm explaining it. So you would see some really, really lazy masters, and even before you get into what Dave's doing with the Spintron, because the Spintron will tell you far more than what just, you know, what your cam spec guys will tell you on, you know, where it is, depending what their initial is, whether it's a 6 thou or some guys 10 thou, whatever it may be, and you're at 50. But if you look at the trailing distance in that, we could have a 260 at 50, but it might have 300 or 295 or 310, and that's that trailing ramp. Yes, it's soft on valve train, but some of them are just too long, and this kills dynamic compression. And again, this is what we've seen with our 1 and 2Js and our RB camshafts. And I think it was turning point that I was getting into. Just playing with the LSA, we were able to move the power curve over 1,000 RPM and just fill this curve out. And again, I think it ended up making about 1,000 horsepower at 30 PSI on one of our customers' 2Js, but he was tuning that. So we're going to cover a bit of that today, how the whole chain of the camshafts work with compression, and that holistic setup, that from intake valve timing. And we're going to go through what we prioritize as far as intake valve opening events, closing events, and so on. So yeah, let's get into it. And the first thing we're going to cover is something from Darren Morgan. So let's do it. All right, guys, so we're going to talk about the horsepower chain. This comes originally from Patrick Hale, but I actually got taught it by Darren Morgan, so thanks goes out to Darren. He actually includes this in his induction training, induction series, so if that's something you're interested in, reach out to Darren Morgan. I'm sure he can help you out with that. But I'll step to the side. This is what we're looking at, basically. So what Patrick Hale did, and another legend in the industry, and I think he was involved in early Pro Stock and NASCAR and so on, but rather than talking about a 4-stroke cycle simply, he broke it up into the events that are actually happening. So our valve overlap, our intake pumping, our intake ramming, our compression cycle, our burn speed, then our expansion, our exhaust blowdown phase, which is a huge one, exhaust pumping, etc., and with valve events. Again, I picked this one up from Darren. It'll make more sense when we start looking at the actual wave harmonics or pressure and velocity, but this will help you understand the complexity behind a camshaft and how it actually relates, especially with the blowdown event. And Darren's talked about this a lot, and a lot of people don't realize it. Generally, most engines by mid-bore, you're blowing off that power. You're really only using about 30 to 40 degrees of the top cylinder to use the force. And because we also need to remember that the piston doesn't go down the bore evenly. the piston will start off slow at TDC because we have a dwell depending on rod length, and then the piston accelerates to mid-bore and then slows down after that and will turn back around. So we're actually blowing it off and then allowing that expanding gas to rush out the pipe and cause that exhaust pumping, that high velocity that we'll see down. But what we need to do is make sure this point, when we blow it down, is at the right point that we catch the wave. And by that I mean that, remember, the piston needs to turn around and come back up. And then we want that compression of that piston rising to help carry the exhaust velocity. And you'll see a little dip in the velocity wave, and that's usually BDC. But if that dip starts dropping right down and then starts to pick back up again, we missed the mark. We opened it too early. And opening it too early, you're fighting cylinder force. Because remember, we're fighting a hell of a lot of cylinder pressure there. If you do open it too early, then you're smashing camshafts, you're ripping the nose off the cam, you're snapping camshafts. There's all sorts of problems that can come into that. So we really need to understand how important our blowdown phase is, the point of opening. So that's not the most important part, but it's a very important part. Again, we'll break it up into different areas. Our most important part, I would say, would come down to our intake opening event. And again, this is going to be based off our exhaust closing event because that's going to set our LSA. But remember, we're opening the valve as the piston's coming up to TDC. And this is why wave tuning is so important, because we have no inertia, we have no piston drawing mechanism. So the piston hasn't gone down the bore at all yet to create the negative pressure needed for the atmosphere to fill it. So we're relying on a high pressure wave landing at the back of the valve. So the instant that valve opens, even though the piston's still coming up, the exhaust valve should be in its negative phase. So it's now creating a negative pressure because the velocity is starting to fall. This is creating a suction on the induction system. And also, if we've tuned the pipe size right, then it's also sending a rarefication wave in, a negative wave into the chamber. Right at the same time, the intake valve is opening as the piston's coming up, and we have this high pressure cleanse that will just push all that burnt gas out, all that inert gas that is burnt. We don't want any of it in there. We want a clean cylinder. The cleaner it is, the more horsepower we're going to make for the next cycle and so on, right? So these are probably most important is the valve opening and closing event, and then we get on to the exhaust event. And the intake closing event is dictated by the runner length as well, and this is what a lot of people miss. With a suboptimal runner, so a runner that is shorter than, say, our third harmonic, if we're targeting it properly, needs to be shorter, needs to have less duration, closed earlier, because we can't develop, one, the inertia, and we can't develop the positive wave that also lands as we're trying to close the valve, right? So that's another aspect we have to look at. So our intake closing event will be dictated by our runner, by our CSA, and by our velocity. So this is why I don't like a lot of camshafts, and in the next series we might get into different calculators that calculate what's the optimal cam timing. I know I think Dave Vizard's got one. There's a couple there we'll look at. If they're not taking into account velocity, inertia, and wave tuning, they're really missing the mark by 2, 3, 5 degrees even. So they can leave a lot of horsepower on the bench. So I want to talk about that as well as we get into it. But yeah, again, I thought I'd share this. It's a very, very old principle. Again, I learned it from Darren Morgan, but it's a principle that might help you understand everything that's happening with the ramming, the compression cycle, the burning, and then the expansion, our blowdown phase, our pumping phases, the velocities running down the pipe, our overlap, and the correlation between these two, which is really, really important. This is why I say the LSA needs to be based on the type of chamber you have, right? And also the RPM point you're targeting, because one LSA isn't right for all RPM. Just like a camshaft only works at 7,821. Wherever the point is, each side of that is always a compromise. That's why variable cam timing is such a blessing, because now we can vary LSA and timing and duration and stuff like that, so that we can carry torque longer, have a wider torque band, have a wider power or horsepower band as well. Because generally in our race engines, our power band is 1500 RPM, 2000 with EFI. It's not very wide at all. So with variable valve timing and variable everything, LSA, duration and lift and everything they've got now, we can have far broader horsepower curves and far broader torque curves, which makes it easy. But yeah, if you're dialing in, you have fixed camshafts, that LSA is going to work really, really well at a specific area, maybe 1,000, 1,500 RPM window. And that's what you need to tune to. And again, if the LSA is right, then we have to get the closing and the opening events of those other mechanisms that's going to feed the dynamic and everything else that goes into it. So I'm going to clean the board off, and we're just going to look at some wave harmonics to help you understand exactly what we're talking about here. Let's do it. All right, so you've heard me talk about pressure differential and how important it is right throughout this induction series. The camshaft is no different, and the whole point of optimizing camshaft timing is to optimize this pressure differential. So we've got a quick diagram on here. Excuse the mess, I'm not an artist. Pressure ratio, atmospheric pressure, and what we're trying to do is create these pressure differentials and make benefit of it. So power, exhaust, intake, compression. Here's our LSA and overlap. Our positive wave we want arriving. So here's our pressure differential between intake and exhaust. We want the intake pressure higher than the exhaust pressure. If we don't get the pipe size right, or if we don't get the wave tuning right, this will be in a low. If this line is under the exhaust at this critical event, then we're not going to clear the cylinder properly. And this is where LSA plays into that. This is where ram tuning comes into it. This is where the length of our induction comes into it. All super, super important into your cam timing. And our other event, which is also very important, is our intake closing event. Same thing. We want the exhaust to create a pressure differential between the two. So the intake pressure should be much higher than the exhaust pressure. Again, this helps us fill the cylinder on our intake valve closing event. And again, like I was talking about in the other video, if we can start stacking those air molecules up on top of that piston as it's coming back up using the inertia, and right before the valve closes, have that positive wave come in and give it that extra little push. And that's what we'll see here. So that's a basic understanding of the pressure waves, and you can really research these in a lot of, what's the word I'm looking for? Software and different stuff. So I was a big person to get into engine analysis like in the 90s, and as soon as like Dyno 2000 come out, I owned a copy of that and play around, and like a lot of people would used to put crap on them, and it was actually something that I found really, really surprising when I did Darren Morgan's induction course. He actually talked about Engine Analyzer, which is another system that I've used and use, and I was very surprised to find him talking about it. And again, it can really help you understand what's actually happening, especially when it comes to all this wave harmonics. Engine Analyzer does this. Dyno Sim, I've got that as well. That does a lot of this for you, shows you the pressures and shows you how the camshaft is affecting those things. Again, they're not perfect, but if you have some real world data to work with, they can really, really help you go forward and understand what's actually happening. Same as pipe max and all that sort of stuff. Calculating those harmonic events will really help you basically get to 95% without all the noise, make you get there really early. And the Dyno 2000 really helped me with that. And again, it's the old garbage in, garbage out, like a computer or tuning or anything like that. You know, if your sensors are sending garbage into the ECU, forget about trying to even tune the car. It's all about how well you use the system. And just don't lie to yourself. If the head flows this much, that's what you put in the system. And the early dyno 2000, that's when I started on, and I could remember even back then, like early 2000s, we would put a combo together, and I was doing street combos and different bits and pieces, and we actually did one for Frank's big block, and on the analysis it come up at like 626 horsepower, and we put this thing on actually Sid's dyno, of all dynos, and it was pretty good dyno. And I think with a couple of jet changes, and I think the second pull, it went 627 horsepower after I'd had an absolute nightmare fight with the exhaust guy who had paired cylinders wrong, and this engine wasn't making horsepower, and the customer's at me going, Jake, what have you done? And I'm like, fucking get the pipes right, so I swear. Get the pipes right, otherwise this thing can't breathe. Anyway, we end up getting Stewie involved with it, and he did a proper set of exhaust to the specifications that we needed, and we got it on Sid's dyno, and first pull, because he wanted a 600 horsepower big block, pump fuel. It was nothing special. Iron headed, pump fuel big block, flat tappet camshaft, cast iron heads that I'd tickled, nothing crazy, just a bowl job. Victor Jr. 850 or 950, something around there. And as I said, 1025 to 1, 256, 580 lift, 260 on the exhaust on 110, nothing crazy. And yeah, first pull on Sid's dyno after we got a few things sorted out, ended up at 627. So it made a horsepower more than we did on the simulator. So I really gained some respect for these tools even back then. They're far better now today. I think Engine Analyzer reads a little bit high, but again, if you just use it as a tool to see if you're going forward or backwards, they're great tools. And I was very surprised to see Darren Morgan talk about this, and it gave me confidence, because I had a few people say, "Oh, why would you use those stupid things?" Same like when we were twin turbo and V8s. People used to say, "Oh, V8s don't like turbos." Well, look where we are now, guys. So yeah, these are really great tools, especially if you want to learn about an engine and cam timing and how LSA affects things and duration and everything like that. Especially if something's got a little bit of wave analysis that will give you this data, you can really see where the camshaft's coming into its sweet spot. And if you have something real world to compare it to, you know what's going to happen to that camshaft if we add 2 or 3 here, or pull 2 out there, or widen the LSA, and it'll really help you. Like for me, I was able to leapfrog my understanding with these sorts of software. So I find it quite naive now when I look back at anyone that went, "Oh, they're crazy," And I remember one guy that worked at Rocket Industry, old bloke, I can't remember his name now, and I was telling him how good he goes, "Man," he goes, "some of this new stuff," he goes, "it's the key. It's going to be the future," and it is now. You look at CFD and everything. 95% of the work is done on that now, and that's the key. And good analysis and good software is no difference. A lot of our cylinder heads now, we're analyzing with software. It gets us 95% there before we even put it on a flow bench. I'm designing cylinder heads and ports all on mathematics, and we can get them like 97%. You put them on the bench and it's like, that's damn close straight off the bat. And I've heard a few other really, really good head guys, not saying I'm a great head guy, but some absolute geniuses in the head game, and they know what valve size, what CSA, what this, and it gets them 99%. They just know, if the CSA is right, the shape really doesn't matter depending on, line of sight, what you can move and stuff. It's going to affect different things, the chamber and so on. But at the end of the day, if you're getting that airspeed right, you get using inertia, and you start getting cam timing right, you can't not make horsepower. So anyway, guys, next week we might hit different calculators. Maybe we'll review Dave Fizard's one and a couple others, and start getting into what actual duration and how we go about selecting a camshaft. All right, see you guys.